far beyond the orbit of Neptune, where sunlight arrives as little more than a bright star against the cosmic dark, something ancient stirs. It is a comet, designated 3I Atlas by those who first noticed its presence through telescopes on Earth. The I stands for interstellar visitor not born within the Sun's gravitational embrace, but somewhere else entirely, in the space between stars. It has traveled for millions of years, perhaps longer, crossing distances so vast that human timescales dissolve into irrelevance. Only now, as it falls inward toward the Sun, does it begin to wake. The comet's nucleus measures perhaps 2 kilometers across, though exact dimensions remain uncertain. It is not a sphere but an irregular lump, tumbling slowly through the void. Its surface is darker than coal, blackened by cosmic rays and the slow chemistry of deep space. For eons, this object has been frozen locked in temperatures just a few degrees above absolute zero, where molecular motion nearly ceases, where even helium would solidify given enough pressure. But now, distance decreases. The Sun's gravity pulls gently but inevitably. And with each passing day, photons arrive in slightly greater numbers. Somewhere in the comet's structure, embedded within ancient ice, are molecules that predate the solar system itself. Water mixed with carbon monoxide, carbon dioxide, methane, ammonia, simple compounds frozen in ratios that tell stories about the nebula from which stars form. There are also complex organics, the carbon-based molecules that form in interstellar clouds when ultraviolet light and cosmic rays break apart simpler substances and reassemble them into larger chains. Scientists suspect that comets like this one carry prebiotic chemistry, the raw ingredients from which life might eventually emerge on distant worlds. It took billions of years for these molecules to arrive here, drifting through the galaxy's spiral arms, surviving shock waves from supernovae, persisting through the long dark between stellar nurseries. The comet does not know it is being observed. Instruments on Earth and aboard spacecraft scattered through the inner solar system track its trajectory with precision. They measure its brightness, analyze the light reflecting from its surface, search for the first signs of activity. Because even though the comet remains far from the Sun, the warming has already begun. At these distances, sunlight is weak, only a fraction of what Earth receives, but it is enough. The surface temperature, once hovering near 30 Kelvin, begins to rise. 50 Kelvin. 70. At around 100 Kelvin, carbon monoxide ice starts to sublimate, transitioning directly from solid to gas without passing through a liquid phase. It is a process so gradual that no eye could witness it, yet instruments designed for such subtlety detect the change. A faint haze appears around the nucleus, invisible to human vision but apparent in infrared wavelengths. This is the beginning of the coma, the comet's temporary atmosphere. Gas molecules escape from the surface, freed from their frozen prison, expanding outward into vacuum. They carry with them tiny dust grains that were embedded in the ice, particles smaller than the width of a human hair. These grains scatter sunlight, creating a diffuse glow that extends thousands of kilometers in all directions. The coma grows slowly, fed by sublimation that accelerates as the comet continues its inward journey. Within weeks, the coma will span a volume larger than Jupiter. Though its total mass remains negligible, less than the air in an average-sized room, there is something quietly absurd about this. An object that spent millions of years in silence, traveling through the empty spaces between stars, now announces itself with exhalations of gas and dust. Only took a few million years to make an entrance. The comet itself remains indifferent, governed entirely by physics, by temperature gradients, vapor pressure, and gravitational acceleration, it does not choose to outgas. It simply warms. Scientists study the composition of the coma using spectroscopy, breaking the reflected and emitted light into its constituent wavelengths. Each molecule absorbs and emits light at characteristic frequencies, leaving fingerprints in the spectrum. Early observations reveal water vapor, as expected, but also unexpected abundances of carbon monoxide and nitrogen-bearing compounds. The ratios differ from those seen in comets born within the solar system, hinting at formation conditions in another stellar neighborhood under different pressures and temperatures. Exactly where this comet originated remains a mystery. The Oort cloud. The vast spherical shell of icy bodies surrounding the Sun contains both objects native to the solar system and those captured from interstellar space over billions of years. Distinguishing between the two requires careful analysis, and even then, certainty eludes. As the coma expands, it begins to interact with its environment. Space is not truly empty. Even in the regions between planets, there exists a tenuous medium, the solar wind, a continuous outflow of charged particles from the Sun's corona. This wind flows at speeds between 300 and 800 kilometers per second, carrying with it the Sun's magnetic field, stretched and twisted into a complex structure called the interplanetary magnetic field. The solar wind fills the heliosphere, a bubble of solar influence extending far beyond the planets, into the realm where interstellar space begins. The comet, with its growing coma, represents an obstacle to this flow. Gas molecules released from the nucleus are neutral at first, electrically balanced with equal numbers of protons and electrons, but ultraviolet light from the Sun quickly ionizes them, stripping away electrons and creating positively charged ions. These ions respond to magnetic fields. They cannot simply drift through the solar wind as neutral molecules might. Instead, they are picked up, accelerated, and carried along by the moving plasma. The process is not gentle. It is a collision between two states of matter, the comet's slow exhalation and the Sun's relentless outward breath. Instruments aboard distant spacecraft begin to notice something unusual. The solar wind, which normally flows with relative uniformity at these distances, shows fluctuations. Density increases briefly. Velocity drops. Magnetic field lines kink and twist in ways not predicted by standard models. The comet, still millions of kilometers from perihelion, is already leaving its mark. Only a few kilometers of ice, and already the Sun's river bends. The heliosphere, vast beyond comprehension, adjusts itself around this tiny visitor. And the comet, tumbling in darkness, continues to warm. The nucleus itself is a museum of deep time. Within its ice, preserved as if in amber, are materials that have remained chemically unchanged since before the Sun ignited. When the solar system was only a rotating disk of gas and dust, 4.5 billion years ago, the region beyond Neptune remained cold enough for volatile compounds to freeze. Water ice, of course, but also methane, ammonia, and more exotic substances clathrates, where gas molecules are caged within crystalline water structures, preserved under pressure. These ices accumulated slowly, grain by grain, building bodies that would become comets. But 3I Atlas is different. Its trajectory, when calculated backward through time, does not originate within the solar system's planetary disk. The orbital parameters are wrong, the inclination too steep, the eccentricity too extreme. This comet arrived from somewhere else, carrying ice formed in another star's nebula, under different conditions of temperature, radiation, and chemistry. The precise differences remain subtle, detectable only through careful spectroscopic analysis. But they are their isotopic ratios that do not quite match, abundances of trace molecules that deviate from solar system norms. Scientists describe these objects as time capsules, and the phrase is accurate but also insufficient. A time capsule is intentionally sealed, meant to be opened. The comet preserves nothing deliberately, it simply froze, remained frozen, and now, by accident of trajectory, crosses paths with the Sun and begins to thaw. The information it contains about the early universe is incidental, a byproduct of chemistry and circumstance. Only took 4 billion years for anyone to notice. The surface of the nucleus is not smooth. Sublimation does not proceed uniformly. Where sunlight strikes directly, ices vaporize more rapidly, creating pits and valleys. Where shadows persist, ice remains intact, forming cliffs and overhangs, over multiple orbits if the comet were to make multiple orbits, which 3I Atlas will not. These features would evolve, the landscape gradually eroding away until nothing remained but refractory dust and rock. But this is the comet's first passage through the inner solar system, at least in recent epochs, and its surface still retains most of its original volatile inventory. Embedded in the ice are dust grains, particles that formed in the atmospheres of dying stars and were expelled into space. When massive stars reach the end of their lives, their outer layers expand and cool, creating conditions where atoms can condense into solid particles, silicates, carbonaceous material, tiny crystals of various minerals. These grains drift through the interstellar medium, sometimes for millions of years, until they encounter a molecular cloud and become incorporated into the next generation of star formation. Some of the grains in 3I Atlas may have originated in stars that died before the Sun was born, making them not just ancient but pre-solar, older than the Earth, older than any rock in the solar system. When the comet outgases, these grains are released along with the vapor. They are too small to fall back to the surface. The nucleus has almost no gravity, so they drift outward, pushed by the pressure of sunlight itself. Photons carry momentum, and when they strike a dust grain and are absorbed or reflected, they transfer that momentum, exerting a tiny but persistent force. Over time, this radiation pressure pushes the dust grains away from the Sun, creating the comet's dust tail, a separate structure from the ion tail. The two tails often point in slightly different directions because they are shaped by different forces. The dust tail follows the comet's orbital path, curved by the grain's initial velocity, while the ion tail points directly away from the Sun, dragged by the solar wind. The dust grains themselves are not inert. Their surfaces are coated with organic molecules, carbon chains, sometimes ringed structures like polycyclic aromatic hydrocarbons. When ultraviolet light from the Sun strikes these molecules, it can break chemical bonds, creating reactive fragments called radicals. These radicals can recombine in new ways, forming more complex molecules. In the diffuse environment of the coma, where densities are extraordinarily low, chemistry proceeds at a glacial pace, but it proceeds nonetheless. Laboratory experiments have shown that similar processes, given enough time, can produce amino acids and other prebiotic compounds. Whether such synthesis actually occurs in comet comae remains an open question. One of those quiet mysteries that persist at the edges of what instruments can detect. As the comet continues inward, the rate of sublimation increases. At 4 astronomical units from the Sun 4 times. The Earth-Sun distance water ice begins to sublimate in addition to the more volatile carbon monoxide. Water vapor becomes the dominant component of the coma, and the outgassing rate jumps by an order of magnitude. The coma expands to hundreds of thousands of kilometers in diameter, though it remains nearly invisible to the naked eye. Only through long exposure photography or sensitive instruments can its full extent be appreciated. To an observer on Earth, if they could see it at all, the comet would appear as a faint smudge, indistinct, easily overlooked. Yet the comet's influence extends far beyond what is visible. The gas and dust it releases do not simply dissipate into space. They interact with the solar wind, and this interaction creates structures. The first of these is the bow shock, a region where the solar wind encounters the obstacle of the comet's ionosphere and begins to slow down. Just as air flowing past an airplane wing creates turbulence and pressure waves, the solar wind flowing past the comet creates a shock, front, a boundary where plasma transitions abruptly from supersonic to subsonic speeds, from ordered flow to chaotic turbulence. The bow shock forms at a distance of tens of thousands of kilometers from the nucleus, well within the coma but still far from the solid surface. Its exact position fluctuates depending on the solar wind's density and velocity, which vary continuously. Sometimes the shock strengthens and moves closer to the nucleus. Other times it weakens and recedes. Spacecraft that have flown through comet bow shocks have measured these fluctuations directly, recording rapid changes in magnetic field strength, plasma temperature, and particle density. The data reveal a boundary that is not a simple surface, but a dynamic, turbulent zone where multiple physical processes compete and interact. Scientists have known about comet bow shocks since the 1980s, when the first spacecraft encountered Comet Halley, but each new comet provides additional data, and 3i Atlas, with its interstellar origin, offers a rare opportunity. Do comets from beyond the solar system produce bow shocks with different characteristics? Do variations in chemical composition affect the interaction? Early observations suggest subtle differences, but distinguishing genuine anomalies from normal variability requires careful statistical analysis. Only a few dozen comets have been studied in such detail, and 3i Atlas is the first interstellar visitor to be observed with modern instrumentation. The comet does not care about these distinctions. It continues to outgas, continues to warm, continues its long fall toward the sun. Only a visitor passing through, and already the scientists scramble. The universe, as always, offers no commentary. It simply unfolds, governed by equations that describe but do not explain, by processes that occur whether or not anyone is watching. Sublimation is a word that sounds gentle, almost poetic, but the process itself operates at molecular scales where gentleness has no meaning. A water molecule embedded in the comet's ice lattice vibrates in place, held by hydrogen bonds to neighboring molecules. As temperature rises, the vibration amplitude increases. Eventually, the molecule gains enough kinetic energy to break free from the lattice entirely. It escapes into the void above the surface, joining trillions of other molecules doing the same thing at the same moment across different regions of the nucleus. The transition from solid to gas occurs without any liquid intermediate. On Earth, water melts before it evaporates, but that requires atmospheric pressure. The comet's surface experiences near vacuum conditions, pressures 1 billion times lower than Earth's atmosphere. At such pressures, liquid water cannot exist. The phase diagram for water shows a boundary below which the liquid state is thermodynamically forbidden. The comet operates entirely below that boundary, so ice becomes vapor directly, a transition marked by the absorption of latent heat. This heat must come from somewhere. Solar radiation provides most of it, photons arriving at the speed of light and being absorbed by the dark surface material. The surface heats up, and that thermal energy propagates inward through the ice. Though very slowly, ice is a poor conductor of heat. Beneath the surface, perhaps only centimeters or meters down, temperatures remain at their original frigid levels, unchanged by the sun's influence. The comet is thus divided into two regimes: a thin, active layer that responds to sunlight, and a deep interior that remains in thermal equilibrium with deep space. The molecules that escape carry momentum. They do not simply drift away passively. They are expelled with velocities of hundreds of meters per second, determined by the surface temperature. These velocities are far below the escape velocity needed to leave the comet's gravity well, which is negligible anyway. Measured in centimeters per second for a body this small. So the molecules fly outward freely, expanding into the growing coma. They travel in straight lines until they collide with other molecules or are ionized by ultraviolet radiation, processes that occur at different rates depending on the local density and the intensity of sunlight. The coma that results is not uniform. Regions closer to the nucleus have higher densities, while the outer regions are more diffuse. The distribution follows an inverse square law, diluting rapidly with distance. At the nucleus surface, densities might reach 10 billion molecules per cubic centimeter, still a million times more rarefied than Earth's atmosphere. But substantial by space standards, 1,000 kilometers away, densities drop to perhaps 10 million molecules per cubic centimeter. 10,000 kilometers out. Maybe 10,000. The coma extends far beyond where densities can be reliably measured, fading asymptotically into the background interplanetary medium. Within this expanding cloud, chemistry unfolds. Parent molecules, the compounds that sublimate directly from the ice, begin to break apart under ultraviolet bombardment. Water molecules split into hydrogen and hydroxyl radicals. Carbon dioxide becomes carbon monoxide and oxygen. Ammonia loses hydrogen atoms one by one. These daughter molecules then undergo further reactions, creating a cascade of increasingly complex chemistry. Exactly which products form, and in what abundances, depends on the local radiation field, the densities involved, and the timescales available before the molecules drift too far apart to interact. Scientists observe this chemistry remotely by detecting the characteristic wavelengths emitted when molecules transition between energy states. Each molecular species has a unique spectral signature. By comparing observed spectra to laboratory measurements, researchers can identify what molecules are present and estimate their abundances. This is how we know, for instance, that 3I Atlas contains unusually high concentrations of carbon monoxide relative to water, a ratio different from most solar system comets, consistent with formation in a colder environment where carbon monoxide ice could condense more readily. But there are limits to what can be determined from Earth. The coma is optically thin, meaning light passes through it with minimal scattering. So spectroscopic observations integrate emission along the entire line of sight. Distinguishing between molecules near the nucleus and those farther out requires modeling. Assumptions about the outflow velocity and the photodissociation rates. These models are sophisticated, built on decades of research, but they remain models' approximations of reality constrained by incomplete data. Actual conditions within the coma, especially close to the nucleus where densities are highest, remain somewhat mysterious. Spacecraft missions have provided ground truth for a handful of comets, flying close enough to sample the coma directly with mass spectrometers and other instruments. These missions revealed unexpected complexity variations in composition across the nucleus surface, jets of gas erupting from specific locations, diurnal changes as the comet rotates and different regions enter or exit sunlight. 3I Atlas will not receive such a visit. It appeared too suddenly, Its interstellar nature recognized too late to organize a mission, so it remains an object of remote study, knowable only through the light it reflects and emits, through the perturbations it creates in the solar wind, and those perturbations are becoming more pronounced. As the coma grows, as more gas is released and ionized, the comet's interaction with the solar wind intensifies. The ions created by photoionization, mostly water group ions, with smaller contributions from carbon monoxide and other species, are immediately picked up by the solar wind's magnetic field. This pickup process is not gradual. An ion, newly created and initially at rest in the comet's frame of reference, suddenly finds itself immersed in a magnetic field moving at hundreds of kilometers per second. The field exerts a force, accelerating the ion perpendicular to both the field direction and the direction of motion. The result is a helical trajectory, the ion spiraling around magnetic field lines as it is swept away from the comet. But the ion's mass does not disappear. It is added to the solar wind plasma, increasing the local density. To conserve momentum, the solar wind must slow down slightly. For a single ion, the effect is negligible. For the trillions of ions produced every second as 3I Atlas outgases, the cumulative effect becomes measurable. The solar wind begins to decelerate well before it reaches the bow shock, responding to the distributed load of newly picked up ions. This mass loading, as it is called, creates instabilities in the plasma. The picked up ions have different velocities and temperatures than the background solar wind, creating a population of energetic particles that can drive waves and turbulence. Magnetic field lines kink and oscillate. Density fluctuations propagate through the plasma at the Alf-Venn speed, a characteristic velocity determined by the magnetic field, strength, and the plasma density. These waves can accelerate particles to even higher energies, creating a feedback loop where instability begets more instability. Only a cloud of gas, and the solar wind starts to stutter. The heliosphere, ordinarily so uniform, develops wrinkles, and the comet, indifferent, continues to sublimate, continues to release ancient ice into the void, molecule by molecule, grain by grain, as it has done for weeks now and will continue to do for weeks to come. The solar wind itself is an old discovery that still holds mysteries. In the 1950s, scientists debated whether space between the planets was truly empty or filled with some tenuous medium. Eugene Parker, then a young physicist, proposed that the sun's corona, its outer atmosphere, was so hot that it could not remain gravitationally bound. Instead, it must expand continuously outward, creating a supersonic flow of plasma that pervades the entire solar system. The idea met with skepticism. Referees rejected his paper. Only the intervention of an editor allowed it to be published, and, even then, many researchers dismissed it as speculative. But Parker was correct. Spacecraft launched in the following decades confirmed the solar wind's existence, measured its properties, tracked its variations. The wind originates in the corona, where temperatures reach 1 to 2 million Kelvin, hot enough that hydrogen atoms are fully ionized, existing as free protons and electrons. These particles, thermally agitated, move at speeds of hundreds of kilometers per second. The sun's gravity tries to hold them, but thermal pressure overwhelms gravitational attraction. The plasma expands, accelerating as it flows outward through the sun's magnetic field. The wind is not uniform. It emerges faster from coronal holes regions where magnetic field lines are open, extending into space rather than looping back to the solar surface. In these regions, wind speeds can exceed 800 kilometers per second. Elsewhere, where the corona is denser and more magnetically complex, The wind flows more slowly, perhaps 300 to 400 kilometers per second. The boundary between fast and slow wind creates shear layers, regions of enhanced turbulence where the two streams interact. Embedded in this flow is the sun's magnetic field, dragged outward by the moving plasma. In ideal magnetohydrodynamics, the theoretical framework used to describe plasma behavior, magnetic field lines are said to be frozen into the plasma, meaning the field and the plasma move together, inseparable. This frozen-in condition creates a peculiar geometry. As the sun rotates, the field lines connected to the rotating surface are drawn out into spirals, like water streaming from a rotating sprinkler. The resulting pattern is called the Parker spiral, a structure that extends throughout the heliosphere, its pitch angle depending on the radial distance from the sun and the solar wind speed. At Earth's orbit, the field is neither radial nor tangential, but somewhere in between, making an angle of about 45 degrees with the radial direction. Farther out, the spiral winds more tightly. Closer in, the field is more nearly radial. The comet, currently several astronomical units from the sun, encounters a field that is already significantly spiral, twisted by the sun's 27-day rotation period. This field will drape over the comet, conforming to the obstacle, creating a complex magnetic topology. The solar wind also carries kinetic energy from its bulk motion, thermal energy from the random motions of individual particles, and magnetic energy stored in the field. Energy densities are low by terrestrial standards, but integrated over the vast volume of the heliosphere, the total energy flux is enormous, equivalent to the output of millions of power plants running continuously. Most of this energy simply flows outward into interstellar space, lost forever as the heliosphere expands. But some of it is tapped by processes within the heliosphere, by planets with magnetospheres, by comets with ionospheres, by shock waves and magnetic reconnection events. The solar wind also varies with time. The sun's activity follows an 11-year cycle, during which the number of sunspots, the frequency of solar flares, and the structure of the corona all change. At solar maximum, the corona is complex and dynamic, with coronal mass ejections, vast eruptions of plasma occurring frequently. At solar minimum, the corona is quieter, more structured, with well-defined coronal holes. These variations affect the solar wind at all distances, causing the wind's density, velocity, and magnetic field strength to fluctuate on timescales ranging from minutes to years. Currently, the sun is in a moderately active phase, neither at maximum nor minimum. Coronal mass ejections occur every few days, sending pulses of high-density plasma outward through the solar system. When these pulses encounter the comet, they compress the coma, strengthen the bow shock, and intensify the interaction. Instruments monitoring the solar wind near Earth detect these events and can predict, with some uncertainty, when they will reach the comet's location. The predictions are imperfect. The solar wind is turbulent, and conditions can change unpredictably, but they provide context for interpreting observations of the comet. The comet, for its part, does not respond uniformly to these variations. Its outgassing rate depends primarily on sunlight, which varies smoothly with distance and only slightly with the sun's activity. But the interaction with the solar wind, the bow shock formation, the ion pickup, the magnetic draping is sensitive to the wind's properties. When a dense, fast-moving coronal mass ejection sweeps past the comet, the bow shock strengthens and moves closer to the nucleus. The ion tail brightens as more ions are accelerated. Magnetic field lines compress and reconnect more frequently. Then, as the pulse passes and conditions return to baseline, the interaction relaxes. Scientists have observed such transient events at other comets and found them rich with physics. Magnetic reconnection, a process where oppositely directed field lines break and rejoin. Releasing energy occurs frequently in the turbulent environment downstream of the bow shock. These reconnection events accelerate particles to high energies, sometimes creating bursts of X-rays as energetic electrons collide with neutral gas in the coma. The X-ray emission from comets was itself a surprise when first discovered in the 1990s. Unexpected because comets are cold objects that emit primarily at infrared and visible wavelengths. Only the interaction with the solar wind, only the energy available in the wind's magnetic field, makes X-ray emission possible. At 3I Atlas, these processes are underway. The comet's interstellar origin does not exempt it from the physics governing all comet-solar wind interactions. The same mechanisms operate ionization, pickup, magnetic draping, reconnection, but the details matter. The composition of the coma, with its elevated carbon monoxide abundance, may affect ionization rates. The comet's relatively low activity level, it is a small object, outgassing less vigorously than larger. More active comets may influence the bow shock's structure. These are subtle effects, difficult to disentangle from the natural variability of the solar wind itself. Only a few spacecraft in the right positions, and already the data accumulate. Measurements of plasma density, magnetic field vectors, energetic particle fluxes, the numbers pile up, awaiting analysis, interpretation, the slow construction of understanding from fragments. And the solar wind flows onward, indifferent to the comet, indifferent to the scientists, carrying the sun's magnetic field into the dark. The bow shock that forms around the comet is not a solid boundary. It is a statistical phenomenon, a region where the probability of particle collisions and wave-particle interactions increases sharply. In ordinary circumstances, the solar wind plasma is collisionless particles travel vast distances without directly striking one another because the density is so low. A cubic centimeter of solar wind at Earth's orbit contains only a few protons and electrons, separated by distances far larger than their physical sizes. Collisions, in the classical sense of billiard balls striking each other, almost never occur. Yet the plasma behaves as if it were collisional. Particles scatter, energies thermalize, shock waves form. This apparent paradox is resolved by recognizing that electromagnetic forces mediate the interactions. Charged particles generate electric and magnetic fields, and these fields affect other charged particles at a distance. Waves propagate through the plasma, carrying information about density fluctuations and field perturbations. Through these collective effects, the plasma can act like a fluid despite the absence of direct collisions. The bow shock is a place where these collective effects dominate. As the solar wind approaches the comet, it encounters the cloud of ions being picked up from the coma. These ions, as mentioned, are initially at rest in the comet's frame, but are then accelerated by the solar wind's magnetic field. The acceleration is not instantaneous. The ions gyrate around field lines, gaining velocity perpendicular to the field direction while being swept along parallel to the flow. This creates a ring beam distribution in velocity space, a population of ions moving in a ring around the background field direction. Ring beam distributions are unstable. They possess free energy that can drive plasma waves. The waves grow, extracting energy from the ion distribution, and in turn scatter the ions, spreading them out in velocity space until the distribution becomes more isotropic. This process, happening continuously as new ions are picked up, generates turbulence that heats the plasma and slows the solar wind. The deceleration is gradual at first, occurring over large distances upstream of the comet, but as the ion density increases closer to the nucleus, the deceleration intensifies. Eventually, the solar wind slows to the point where its velocity equals the local wave speed, specifically the magnetosonic speed, which depends on both the plasma temperature and the magnetic field strength. At this critical point, the flow transitions from supersonic to subsonic, and a shock forms. The shock is a thin region, perhaps only a few hundred kilometers thick, where plasma properties change abruptly. Upstream, the flow is fast, cool, and relatively uniform. Downstream, the flow is slower, hotter, and more turbulent. The transition is not smooth, but marked by oscillations and fluctuations as the shock adjusts to varying upstream conditions. The exact position of the bow shock depends on a balance between the solar wind's dynamic pressure and the pressure exerted by the comet's ionosphere. When the solar wind is strong, the shock moves closer to the nucleus. When the comet's outgassing increases, the ionosphere expands and pushes the shock farther out. This balance is never static. The solar wind's density and velocity vary continuously, and the comet's outgassing rate changes as different regions of the nucleus enter or exit sunlight. The shock's position fluctuates by thousands of kilometers over timescales of hours to days. Spacecraft that have crossed comet bow shocks report the crossing as a series of rapid changes in measured quantities. Magnetic field strength jumps by a factor of 2 or 3. Plasma density spikes, temperature increases. Particle detectors register bursts of energetic ions and electrons. Then, within minutes, the spacecraft exits the shock region, entering the downstream environment where conditions are different but still turbulent. Some spacecraft have crossed the same shock multiple times as it moved back and forth, providing repeated measurements of the same boundary from different perspectives. At 3i Atlas, no spacecraft is nearby to make such direct measurements. The interaction must be inferred from remote observations and from monitoring stations scattered elsewhere in the solar system. Spacecraft near Earth, for instance, can detect disturbances in the solar wind that may have originated at the comet. Magnetic field perturbations, propagating outward as Alfvén waves, can travel across millions of kilometers before dissipating. By triangulating observations from multiple spacecraft, researchers can sometimes trace these perturbations back to their source. The process is imperfect. The heliosphere is filled with transient structures, shocks from coronal mass ejections, stream interaction regions where fast and slow solar wind collide, corrotating interaction regions tied to the sun's rotation. Distinguishing the comet's influence from this background noise requires careful analysis and often leaves ambiguities unresolved. A particular fluctuation in the magnetic field, is it from the comet or from a small-scale solar wind structure that passed the monitoring spacecraft? The data alone cannot always answer, yet patterns emerge over weeks of observation. As the comet brightens and its outgassing increases, the frequency of certain types of perturbations in the solar wind also increases. Statistical correlations appear, suggesting a connection even if individual events remain ambiguous. This is how science often proceeds, not with definitive proof from a single observation, but with the accumulation of evidence, the slow convergence toward understanding through multiple lines of reasoning. The comet's bow shock, like all shocks, is a dissipative structure. It converts the ordered kinetic energy of the solar wind's bulk flow into disordered thermal energy, heating the plasma. The second law of thermodynamics ensures that this process is irreversible. Entropy increases. The solar wind emerging downstream from the shock is degraded, in a thermodynamic sense, relative to the pristine wind that approached. Some of the wind's kinetic energy has been permanently converted into heat, which will eventually radiate away into space as photons, lost forever. This energy conversion is not unique to comets. It occurs at Earth's bow shock, at the bow shocks of other planets with magnetospheres, at interplanetary shocks driven by coronal mass ejections. It is a fundamental aspect of how plasmas interact with obstacles. The comet simply provides another example, another laboratory where the same physics plays out in slightly different circumstances. Only a small visitor, and already it heats the sun's wind. The energy is negligible compared to the solar wind's total flux, but locally, at the shock, it matters. Particles gain energy, waves are generated, entropy increases. The universe, as always, moves toward disorder, one interaction at a time. Downstream from the bow, shock lines